Hi everyone, thank you for joining the meeting. I am basically going to give you guys a lecture about what n-body problems are and how quantum computing can be used to solve those problems. This session would be an introductory session. I have tried to include a lot of diagrams in the presentation to make it more interesting. And yeah, I would really appreciate, Kamaya, if you could screen share the presentation, please.
Sure, I hope it's visible to everyone.
Um, could you repeat?
I hope my screen is visible to everyone.
Yes, it is visible. Thank you.
Great.
So today's topic is how quantum computing can solve the n-body problem. I'm basically going to go through the table of contents right now. What are we going to discuss in the presentation today? So firstly, I'm going to introduce myself. My name is Arushi Ahuja. I study in grade 12. I live in India. I have always been interested in knowing more about quantum physics, especially quantum computing. I also have my Medium account where I post articles about different discoveries in physics. My latest article was about the discovery of gravitational waves using pulsar timing arrays. If any one of you have any questions you want to ask me after the meeting, for example, what resources should you refer to study more about quantum computing, or just want to connect, feel free to connect with me on LinkedIn and also have a look at my YouTube channel if you like. On my YouTube channel, which is called Qubit, I basically post animated videos about different concepts of quantum physics, such as superposition and entanglement. So these are the table of contents. So first we're going to talk about the n-body problem, what it is and its significance. Then we're going to move on to studying about quantum computing. So we are not going to go too deep into this, but just have an overview of the basic concepts such as superposition, entanglement, and what makes quantum computing different from classical computing. Then we're going to talk about different algorithms and simulations which are used in quantum computing and which can be used to solve the n-body problem. Then we're going to look at basically the challenges in quantum computing, um, and also the reason why quantum computing is not able to solve the n-body problem for now, but still it has the potential to do so. Um, so lastly, we're going to basically, open the floor for more questions. Any questions you might have regarding anything in the PPT or just in general about quantum physics. So let's start with the first topic, the n-body problem, right? Now, the n-body problem basically involves us predicting different, like individual motions of planets interacting with each other gravitationally. Now, what happens is that if you have studied this in school, that to calculate the gravitational force between two planets, you basically use a particular formula created by Newton, right? But when you are, for example, a scientist, right, and you need to calculate the gravitational forces between many number of planets or n number of planets, your calculations become increasingly difficult to do manually, right? For example, if there are 5 different planets and I choose one particular planet out of them, and I ask you, what is the gravitational force? What is the net gravitational force which is acting on that particular planet from those rest of the 4 planets? You will have to take different equations for each pair and then create the vector sum of it. But when you're looking at, maybe 8 more planets in the solar system, or when you're looking at satellites or other celestial objects, you tend to, feel that the calculation is becoming difficult. So, which is why when even classical computers are used, they're not able to perform those calculations faster, which is why we need a quantum computer in the first place. So I'm also going to read off the slide a little so that you have some reference. So the n-body problem, it was introduced by Isaac Newton, and it remains one of the oldest problems in classical mechanics. So physicists are still trying to figure out how to solve it, they have referred to quantum computing as a potential solution. And understanding the n-body problem basically helps us in many applications, right? As I said. So it could refer to, how to simulate how a galaxy forms or how different satellites move, right? Because there's not only one satellite we may have more than one satellites, right? So how do those satellites move in a particular inertial frame, and how different planetary orbits basically simulate. Now, this is what I was talking about in the first place. So, when you need to calculate the gravitational force between two objects, right? You can consider them as planets for now. You basically pick an inertial frame, right? Frame of reference. And you take two point masses. If you don't want to consider them as planet, you can just consider them as point masses. You calculate the distance between them as well as the distance of them from the particular reference point, right, which is O here. And if you may scroll down, I've also described what an inertial frame is, if any one of you doesn't know. So inertial frame is basically a point of reference, right? So this is a very funny diagram, but what it says is that there is one um, child who is, in a box or in a cart, right, which is moving, and she thinks that she is still. But at the same time, when some other person looks at it, who is not in the cart itself, but standing outside, for them, the child is moving. Now, similarly, when you are sitting in a bus, you aren't moving yourself, right? You think you're sitting still. But at the same time, if someone were to look at you from the road or from the footpath, they might say that, okay, no, you are moving with the bus. So in physics, especially, it becomes increasingly important to describe your situation or the particular system with the help of an inertial frame of reference. Right. So in this case, we took the inertial frame outside of those planets, so we could see whether they're moving or they're not moving or whatever the case is. Now, why does the n-body problem matter, or what is its significance, right? Now, as I said, when you have to calculate just one equation, right, of a gravitational force between two objects, it's very easy, right? You can do it on a piece of paper. But when the number of planets or the number of objects increase, your number of equations increase too, and they increase exponentially. For example, if you have 5 planets, right, in total, and you choose one planet out of them, and you need to calculate the gravitational force between that one planet and the rest of the 4 planets, you have to calculate them individually. So in total, you may have 25 equations, right? Now calculating 25 equations all at once and also keeping in mind the amount of time you take is very difficult. Hence, now I'm going to read off the slide. The complexity arises because each body exerts a force on every other body. And this creates the number of total equations you have increased by a lot, basically exponentially. And the way you can think of it is like you're juggling, right? When you're juggling 2 balls, it's manageable. But the more objects you add onto it, your your mindset into how do you balance each of those objects sort of kind of shatters, or the task becomes difficult. And so here you can consider each ball as a different equation of calculating gravitational force between two objects. Now, I hope this part was clear. So we are basically going to move on to what quantum computing is now, and the different terms we commonly use for it. So two terms which you're going to come across, whether you read different articles on Google about quantum computing, or different, or hear different lectures regarding this topic, would be entanglement and superposition. So we're going to first start how quantum computing is different from classical computing. So whenever you have a classical computer, for example, the computer I am working on right now, it stores information as bits, right? So it could store, for example, let's call like different information like X and Y, right? So it could store X as 0 and it could store Y as 1. But it always stores X as either 0 or either 1. Those two bits can't be stored simultaneously. But in quantum computing, the quantum computer can store a particular set of information, for example, X, as both 0 and 1 simultaneously. So that is what makes it different than classical computing. Now, what happens is because of the information being stored in two separate states at the same time, the way you process that information becomes like exponentially faster, and you can perform a lot of simulations at the same time too. So to read of the slide, unlike classical bits, which are either 0 or 1, qubits can exist in a superposition of states. So superposition basically means something existing as two different things at the same time, right? Now, this allows quantum computers to process a vast amount to process vast amount of possibilities simultaneously. So now what is entanglement? Entanglement is basically linking two different qubits together so that when you make change in one qubit, the same change occurs in the other qubit too. Now, as it's written on the slide, entanglement enables qubits that are interconnected such that the state of one qubit can depend on the state of another, no matter the distance between them. Now, due to superposition and entanglement, quantum computers can perform many calculations at once, offering the potential for exponential speed up over classical computers. Now, just imagine if you have, the ability to store information as two different things at the same time, right? So there would be case one, which is, for example, the information set X is stored as 0, and case two, which is the information set stored as 1, right? Now, you have two different cases, right? And when the number of basically X or Y, so the information sets you increase, the different simulations also are increased, which you can perform. So, case one would be X as 0 and case two would be X as 1. So there are different cases which you can simulate to get much more accurate data for your calculations. Now, how does quantum computing offer us a potential solution to the n-body problem, right? So there are different algorithms and simulations you can use for this. So one such algorithm is the quantum approximate optimization algorithm, right? Or the variational quantum eigensolver. Now, these seem like very fancy names, which they are, but basically what an algorithm does is that it offers you a method to solve a particular problem. So when you go deeper into quantum computing, or when you read more about it, you will come across different algorithms. And so for example, there could be a method which could be used to reduce quantum noise in simulations, right? Now that particular method would be considered as an algorithm as well, right? So these are basically developed to tackle complex optimization and simulation problems. Whenever you're performing a quantum simulation, there are always like at least two parts you need to consider. One is the amount of errors you're getting, which are known as noise, and the other is how accurate your data is, right? When the more like fine-tuned your data is to different conditions, which is basically known as optimization. Now, quantum computers can simulate these situations exponentially faster than classical computers, which is why we use them. Now, the challenges and future prospects, right? As I said, even though quantum computing does offer us a potential solution to solve the n-body problem theoretically, it has not solved it right now. So basically, we're going to learn about what is stopping us, right? Now, current quantum computers are at the early stage of development, as you know, and they can't really solve large n-body problems, right? So as I said, exponential amounts of data to be solved just in a very short duration of time, it is not possible yet. But we do know that this is possible in theory, and we have the methods for it, as well as the other challenges, challenge that we are facing now, which I mentioned earlier, is quantum noise, right? So basically, the different errors you're getting. And the other is decoherence. Now, scientists are working on different error correction methods or different algorithms to tackle error correction, which can make these quantum computers more efficient. and can finally solve the n-body problem. So I really don't know, but maybe in 10 years' time, we might have a different method. But almost like every day, when you come across a different research paper on any particular site, you come across different algorithms which researchers are trying to develop to make computing better than it was maybe 1 year ago. And IBM is a top company which is working to do that. Now, I think I finished the presentation a bit early, but we've concluded the presentation, and I hope you understood everything. There weren't many formulas which I put in the presentation intentionally because I thought this may make the introductory session a bit complicated, and you might lose interest. But yeah, please ask any questions you'd like.
I had a question.
Um,
Like how many n-body problems, how many n-body problems actually exist? Like, is there a specific number or?
So I honestly don't think that there is just like a finite amount of number, for example, like three n-body problems. I don't think that is there. Um, like as much as I've read about it, I don't think so. But there are different kinds of n-body problems in the sense in different fields, right? So for example, um, n-body problem, like let's simplify this, right? So n-body problem basically means the complexity of calculations you come across when you're considering n number of bodies, right? So if I'm calculating, for example, the gravitational force between n number of objects, I might say n body problem in in gravitation, right? Or in plan gravitational forces. The other n body problem could be there, like I'm just talking about the applications here, could be when you need to calculate the motion or the velocity of a particular satellite outside of space. So you don't just have one satellite, you might have 24 satellites, right? I don't remember the exact number. But so n-body problem, you come across an n-body problem there. So I really am not sure of the exact number of n-body problems, but I could tell you more about the different um, areas of study you come across an n-body problem. So as I said, calculating the velocity of a satellite, you need to simulate, for example, the movement of a particular galaxy through space, right? Or you need to calculate the gravitational force between like n number of planets. Does that answer your question?
Yeah, okay. Thank you.
Thank you. If any one of you, like, if anyone else wants to ask any questions, feel free to do that. I could also talk more about the different resources you could refer to, if you'd like.
Yes, please. Yeah.
So you could, if you want to learn more about quantum computing, I would really, suggest that you go through IBM's website um, and read more about quantum computing. They publish different blogs about, how to optimize quantum noise or, different algorithms that have come up in the last 5 years. IBM also launched a programming language called Qiskit, which is basically used to simulate different, basically different, quantum computing problems, right? And Qiskit is another language, so you can consider it just as Python or other programming languages. And they have a particular free course, which is on YouTube as well as on the IBM website. So if you have time to join that, or just like spend 30 minutes each day learning it, I suggest it's very good. I myself, you know, completed that course last summer, so in grade 11, and it was very beneficial. So yeah, that provides you an introduction to quantum computing. Um, the other thing would be to just go like through different um, university lectures on quantum physics, not quantum computing, but quantum physics. So by that I mean like learning more about entanglement, superposition, what is decoherence, right? And a lot of the lectures that you will find might also be lectures like from written as chemistry lectures more than physics lectures. but I think they both would give you a good overview over it. I am not sure of a particular book to suggest you because most of my learning was from different research papers, and IBM and different websites like that. But if you think that you'd benefit from reading from a book, I believe that there's a book called Quantum Computing for Dummies, which is very good, because it treats you as like a beginner, as a total beginner when you want to learn about the subject. So even if you don't know, how to, for example, if you don't know Qiskit, if you don't know what superposition is, you still can learn from that book and get to a very moderate level of understanding. Anyway, then you can continue learning Qiskit from IBM. They have a particular summer program each year, so you can join it online. And if you have any questions regarding the other resources you want to refer to, and just, any questions regarding, for example, how did I come across quantum computing and how did I learn from it, feel free to, ask that right now. Or if you don't want to, you can reach out to me on LinkedIn as well. Kimaya would be posting my LinkedIn ID, I think. Actually, it's on the presentation itself. So if you want, you can take a screenshot. So someone has posted a question of the chat. Maniba, hi, I have a question. What is the significance of the N-body problem in modern science? That's a good question. So we talked about it in slide 3, but I don't think it was as detailed as it should have been. I apologize for that. So as I said, the N-body problem in modern science. So in modern science, basically, you're working towards, of course, you are programming a quantum computer, but you also need to sometimes calculate the particular movement of a galaxy, right, through space, or the motion of a satellite, or the motion of a planet, right? So when you're doing all that, you do need to not just perform calculations for one planet, but maybe a set of different planets, right, as I said. So if I have one planet here and there are 4 different planets here, right, so 1, 2, 3, and 4, I would, for to calculate the total gravitational force exerted on this planet by all these 4 planets, I need to take the individual gravitational force, right, for each pair, right? So planet 1 to planet 2, planet 1 to planet 3, and so on. And a lot of the times, this task is very difficult to do on a classical computer, because what I am explaining to you right now, in terms of like you just have 5 planets, it's very simplistic, right? You might need to factor in different attributes as well. So you might need to consider the charge or ions, right? Which deal more with chemistry, but you might need to consider those attributes as well, which is why using a classical computer is not enough. And more than that, it basically creates an n-body problem, because you have n number of objects that you don't know. So, for example, if you have a particular asteroid, right, or any other celestial object, you might have a number of objects that you can't really calculate or work on manually, right? So they might not be a finite number like 10 or 12. It might be 99 or 80, right? Which is difficult to perform, for which it is difficult to perform calculations on like a classical computer or manually. I hope that answers your question. Um, would be,
So,
oh, sorry.
Miss, or Madam,
So Ishita is asking that would you say quantum computing is related or relevant to computer science? I do think so, because I myself am very interested in computer science more than physics, which is why I like quantum computing. But related, yes, because you are, for example, as I said, you're learning a particular programming language such as Qiskit, right, which is from IBM. So it does involve basics of programming, like logical thinking, problem solving. So it is related to computer science, but is it solely, like, if you are a quantum computing scientist and you are working somewhere, would I say that you are just working in computer science? Not really. You do need to have an understanding of physics, and like especially quantum physics, right? So it is related to computer science, but I won't say it is entirely that. I hope that answers your question.
So, excuse me.
Hi, Ahmed.
Hi, could I ask you a question?
Sure.
Is there like an specialty field that combine both AI and quantum computational? What is it? So, is there any specialty or any field combine them?
So I personally was very curious about this, and I read more about AI and quantum computing and combining both of them. Like I think I really don't remember like if there is a name for the field, but when you are creating quantum simulations, as I said, on different platforms such as Qiskit, you might want to automate the process using AI, and I think some simulations have been done using that. So people have used Python and different libraries such as TensorFlow to automate those particular simulations. But but I do think that yes, a field like that exists. But I don't think there's a special name for it. It's just like it's just quantum computing or automated quantum computing. Although the scope for AI for performing quantum simulations is moderately large because when you're working on a large amount of data, you might perform or write code for a particular simulation which is same for let's say 6 different situations, right? And you may want to automate that process. So you can use AI to do that. I also think that it would be a good summer project for one to do who is interested in quantum physics. I hope that answers it.
Yeah. So, and also the main concepts about quantum computing, that's the quantum computing provide like visualization more accurate than the classical computer, isn't it? Or is that
What simulations are you referring? What visualizations are you referring to? Could you elaborate on that? Like, is there a
like
particular?
for the data? Maybe because the quantum computing like storing like a number between 0 and 1 and the classical computer also store the the specific 1 or on 0.
So yeah, to answer your question, I think you're asking the difference in how information is stored in bits in classical and quantum computing, I think. So basically in
Yeah.
classical computing, what happens is that, for example, if this is like, I'm really going to simplify this, right? So for example, this is your memory storage, right? In a particular classical computer. Now this is divided into different bits, right? Now, when it is divided into different bits and you need to feed information to your computer. For example, I want to give my computer a particular information set called X, right? I have just put a variable there, X, you can put it as Y. Now, in a classical computer, depending on the amount of, for example, characters that variable has, or hexadecimal, that information set is stored as either a 0 bit or a 1 bit, right? But it is either of these situations, right? Not both at the same time. Which is why the calculations so when you are calculating something, you are using some amount of information, right? For example, if I want to calculate the gravitational force between two objects, I need to know like hypothetically the mass of object one and object two. Now, this could be used as an information set. Now, when I provide a classical computer these information sets, and when it needs to solve n number of these equations, it does that very slowly because it is storing that particular equation or information set as either 0 or as 1. So it takes a lot of time. Now, when you talk about quantum computing, it stores that information set called X or Y as both 0 and 1 at the same time, right? So in a way, you can think of it as two different situations being considered there. So x is equal to 1 or x is equal to y and x is equal to 0, right? So similarly, when you have n number of equations, you are considering two different situations at once, and they are basically branching out into different number of equations. So the amount of simulations you have, or the amount of data the computer provides you as a potential solution increases. So this is the basic difference, just how information is stored in bits. Does that answer your question?
Yeah, thank you, Miss. I don't see your name, but thank you.
Thank you. So second question, I think Munida is asking, are there any known solutions for specific cases, and what are some methods used to approximate solutions? So I don't read, I mean, as far as I've read, I don't think there's like a solutions in the sense like in the practical sense there's a solution to an n-body problem, because then we won't be reading about the challenges we are facing right now. But solutions, yes, you do come across solutions when you're performing a quantum simulation, which is basically, so I would first need to talk about what a simulation is, right? So a simulation is basically you creating a situation, whether that's on a computer through programming, right? Or just a hypothetical situation, and you define different attributes. For example, if I need to create a simulation of the weather today, I might choose that, okay, how much temperature do I want, or how much moisture in the air do I want? And I put those different values in my program and then create a simulation, right? It could be an actual picture of that day, which is created, or it could be just, the amount of factors, for example, the probability of it, of the day being, of the weather being rainy, or, things like that. So that is what a simulation does. Similarly, when I talk about quantum computing, I might define, like, put those values in different attributes, such as quantum noise, right? There would be information sets which I'm using for the gravitational wave, or basically that information set being stored as 0 or 1 at the same time, and how much time is it taking. So that is how a simulation happens. You have different algorithms, such as the variation eigensolver, which would give you a final value depending on the kind of attribute for which you want the value for, right? So if you want the value for quantum noise, or if you want the value for, I don't know, just like the amount of time it would take to perform that particular simulation, if that makes sense. So yeah, you do have finite solutions, but I don't think there is any set or constant value such as like 5 or 4, which I could say. It really depends on what you're calculating. I hope I explained that well. If there are any more questions, you can ask me. It's feel free to do that.
Wait, so I had a question. So I read about quantum algorithms for my lecture as well. And I came across superposition and entanglement in their applications in the same, but I'm not practically sure of how entanglement is achieved really, because theoretically it sounds, achievable. But I'm not sure of how that can be practically done, because like you're essentially linking two electrons or two quantum particles together. So can you please elaborate on how that's done practically?
I really couldn't hear you well, but are you asking how entanglement can be used practically? Because it's more so a theoretical concept. Was that the question?
All right. So I asked how entanglement is achieved practically.
Okay, got it. So as I said, entanglement for now is a theoretical concept, right? Can it be achieved practically? It would be very difficult. So it's not something like you take two particles here, right? I take two particles and I entangle them. It's not achievable in that sense, but you do need, I would say, like, there is a triple slit experiment, if you would have heard about it. So you I mean I can open it off my browser, but there have been different experiments performed where they have taken two particles and entangled them. By entangle them, I mean that whenever for example, if particle 1 is undergoing a particular change, particle 2 is undergoing the same change too. So entanglement has been achieved in real life, experimentally, but the experimental conditions are very sophisticated. So in that sense, it can be done practically. But when you're looking at entanglement, like just as a theoretical concept, it's very vast, right? But practically, it has been done, it has been achieved, but not to a very, very big extent right now.
Great, thank you so much.
Thank you. So I think it is my time to go because I've extended 30 minutes, but I hope you all understood what we talked about here. I tried to make this PPT as simplistic as possible because I thought it's an introductory session. But yeah, if you have any questions or want to connect with me, you can, reach out to me on LinkedIn. My LinkedIn the profile link is on the slide itself, which is shown to you right now. Also, there's my YouTube channel. So if any one of you, want to kind of learn more about the basics of quantum physics, such as entanglement or superposition, feel free to watch some of the videos. You don't have to subscribe, but if you do like the content, feel free to do so. There also can be like some resources which I might just share with you. So there is IBM Quantum Learning. There is Qiskit, a language which you can learn if you want to. There are plenty of YouTube videos about it. So through Qiskit, you can actually perform a simulation. And more than that, I think you should watch a video called N-Bodies Problem Simulation using Python, which is very interesting. So if any one of you knows Python and wants to do that simulation, I think it's a very cool thing to do. And yeah, so there are different resources you can refer to. And feel free to reach out to me. It was great talking to you all. You had asked some amazing questions, each and every one of you, which I really appreciate. Thank you.
Great, thank you so much for your efforts, Arushi. I really appreciate. And thank you for this wonderful presentation. It was really informative, I believe.
Thank you, Kamaya, for inviting me